Now let's look at solving a collision problem. So what you're going to notice that this is really a multi-step problem. So for example, let's say we have two pendulums. So they're both masses just connected to a rope with length L. Okay, we're going to lift one mass up so that it makes some angle theta with the vertical. We're going to let it go, so it's going to come down, it's going to collide with the second mass, they're going to stick together, and they're both going to rise to, their centers of mass are both going to rise some height h. So now the question is, what is h? Okay, so there's really nothing new in solving this problem that you haven't been doing in the chapters on conservation of momentum and conservation of energy. So with that being said, I want you to take a minute and pause the video and try to solve this problem on your own. And then when you think you've got an answer, or you've been working on it for 15 or 20 minutes and can't seem to get anywhere and are ready to pull your hair out, then come back and watch the video and see if you got it right. Okay, so I want you to do that now. Okay, so let's take a look at how we do this. So as I mentioned before, a lot of these collision problems are really going to have multiple steps. So in this case, the first step is we need to find out what the velocity of mass 1 is before it collides with mass 2. So to do that, we say, okay, well, we know we're going to say that it's up some initial height d. Okay, and we need to find d. So again, we'll call this the point where our potential energy is 0. So our energy of the system is going to be mass 1 times g times d. And so we notice that if this is length L, okay, this vector, this line here, is going to be L cosine theta. So in other words, this distance d, we see that d is really L minus L cosine theta. So when theta is 0, that means cosine theta is 1, so d is 0, and that's the case when it's just hanging down. Whereas if we make theta 90 degrees, then cosine theta is 0, and so d is L, which is what you would expect it to be. Okay, so that means that the energy is really m1g L 1 minus cosine theta. Okay, and then we know that at the end, just before it collides with mass 2, that's just going to be all kinetic energy, 1/2 m1 v squared. And so if we cross out our masses and we multiply by 2, we see that v is equal to the square root of 2gl 1 minus cosine theta. Okay, now how does that help us? Now we look at now we see that there's going to be a collision between mass 1 and mass 2. Because it's a collision, we know that momentum is conserved. So m1v is equal to m1 plus m2 times, we'll call it v prime. So in other words, v prime is m1 over m1 plus m2 times v. So that gives us the velocity after the collision in terms of v, which we already found. I'm not going to bother plugging it in now just to save space. Okay, and then we once again use the conservation of energy, and excuse me, we say that 1/2 m1 plus m2 v prime squared right? So this is the sum of the masses times their velocity right after the collision is going to equal m1 plus m2 gh. Again, because now we're saying once they've collided, they become one mass. And so both masses, so this mass m1 plus m2 is going to be moving initially at the final velocity right after their collision. And then in the end, it's just going to be the sum of their masses has gone up by some height h. So we can cancel out the masses. So we see that h is going to be v prime squared over 2g. Well, this is m1 over 2g, m1 plus m2 times the square root of 2gl 1 minus cosine theta. And so so here we have our answer. Okay, so we can check the units. And so if we do that, we see that we have a mass on top, mass on bottom, so the masses cancel. We see that we have a g outside and a g inside the square root. So this gives us a meters. So this g is going to give us, because it's 1 over g, it's going to give us second squared over meters. And then in here, we have a meter squared, second squared. So this g is going to give us meter squared, because we have a meters times a meter, so meter squared over second squared. And so we see in the end, we're going to be left with just meters, which is exactly what we wanted. So we see that the units check out. I'm sorry, that's not quite right. Sorry, this was supposed to be a v squared, so we shouldn't have that. In fact, I can think I could just go ahead and erase that. Yeah. So this should just be in parentheses. There we go. So now we have something that's just in meters. So there you see an example of where So I was working through this. I was checking my units, and I was like, wait, this part was in a square root, and that wouldn't make sense. We need this to be outside of the square root for the units to cancel out and just give us an overall unit of meters. And so now we have that, and we have our answer, and so that's how you would solve a problem like this.